Right now, as you're watching this, you think you're sitting still. You're not. You're accelerating, constantly, upward, at about 22 miles per hour every second. Wait, that doesn't make sense, right? You're just sitting there, not moving. Here's the thing. Everything you've been taught about gravity is a lie. Not a small lie, a fundamental misunderstanding of reality itself. You think gravity pulls you down? It doesn't. You think the Earth is holding you in place? It's not. You think you understand one of the most basic forces in the universe? You don't. Nobody did. Not for centuries. Not until one man looked at falling apples and orbiting moons and asked a question so simple, so profound, that it shattered our entire understanding of space, time, and reality itself. And when you finally see what he saw, when you really understand what's happening right now as you sit there, the entire universe will never look the same again. Let me show you. The invisible pull. Stand up for a second. Go ahead, I'll wait. Feel that? Your weight pressing down on your feet? That's gravity, right? Earth pulling you down toward its center? Except, what are you actually feeling? Think about it. Really think. The sensation in your feet. That's the floor, pushing up against your soles. That pressure, that force you feel, it's all upward pressure, the floor pushing against you. This mysterious downward pull everyone talks about, you've never actually felt it, not once in your entire life. You only feel the push, always up, never down. Weird, right? Here's something weirder. Drop your phone right now. Don't actually do it, but imagine it. It falls. Okay, gravity pulls it down. Simple. But here's the thing. The phone and a bowling ball fall at exactly the same speed. Drop them both in a vacuum. They hit the ground at the exact same instant. The bowling ball is way heavier, so gravity should pull it way harder, right? And it does. The gravitational force on the bowling ball is much stronger, but it also has more mass, so it's harder to accelerate. And these two things cancel out perfectly every single time for every object ever tested. Why? The instant message problem. Now look up at the moon. Right now, the moon is falling toward Earth. It's been falling for 4.5 billion years, but it never gets any closer. It just circles, forever falling, never landing. What kind of pull works like that? And here's the really crazy part. According to Newton's laws, if you could somehow move the Earth right now, the moon would feel it instantly, immediately, across 240,000 miles of empty space, faster than light. Instantaneously. How?
What carries that message? What's the mechanism? What reaches across 250,000 miles of vacuum and says, "Hey, Earth moved, time to adjust your orbit"? Newton himself couldn't answer this. He called it action at a distance and straight up admitted he had no idea how it worked. He just knew the math was beautiful. The predictions were perfect. So everyone stopped asking uncomfortable questions. Big mistake. Let's rewind. Year 1600. Nobody understands how planets move. Copernicus said they orbit the sun, sure, but how? What paths? Enter Tycho Brahe. This guy was obsessed. He built an observatory and spent 20 years, every single night, recording planetary positions, writing down angles with brass instruments, measuring to fractions of a degree. Why such insane precision? Because you can't understand nature by guessing. You have to look, measure, write down exactly what you see. When he died, his data went to his assistant, Johannes Kepler. The 8-minute difference. Kepler wanted to figure out the shape of planetary orbits. He tried circles first. Made sense, right? Circles are perfect, beautiful, and his predictions were close, really close. But Mars was off by 8 arc minutes. That's 8/60ths of a degree. Barely anything. Most scientists would have called that measurement error. Close enough, but Kepler knew Tycho. That man didn't make 8 arc-minute errors. If the data said 8 minutes, it was 8 minutes. So Kepler threw out his entire theory, started over. Years of brutal calculations later, he found it. Ellipses. Planets move in ellipses with the sun at one focus. Perfect match. Not 8 arc-minutes off. Perfect. Beautiful. But it raised a bigger question. Why ellipses? The rolling ball revolution. Meanwhile, in Italy, Galileo was doing something that seemed almost stupid in its simplicity, rolling balls down ramps. But watch what happens. Roll a ball down an incline, it speeds up. Let it roll onto a flat surface, it keeps going, doesn't stop immediately. It gradually slows down from friction. Now imagine perfect conditions. No friction, no air resistance, nothing. What happens? The ball would roll forever. Same speed, same direction, forever. This broke people's brains. Surely motion requires a continuous push, right? Surely things naturally come to rest. No, that's backwards. Motion is natural. An object moving in a straight line doesn't need explanation. That's the default state of the universe. What needs explanation is change. Slowing down, that's friction. Speeding up, that's a push. Changing direction, that's a force. This is inertia, and it creates a massive puzzle. Newton's revelation. Young Isaac Newton saw it clearly. Planets should move in straight lines. That's their natural state. But they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them every single instant. What? He called it gravity. Universal attraction between any two masses. The force depends on mass and distance. More mass, stronger force. Greater distance, weaker force. Specifically, the force drops with the square of the distance. With this one principle, everything clicked. Why ellipses? Because planets are falling toward the sun while simultaneously moving sideways. The combination creates elliptical paths. Why does the moon orbit Earth? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing it. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same force, same law, just different scale. The ultimate test. Newton did something brilliant. He calculated how much the moon falls every second, how much its path curves away from a straight line. Then he calculated how much objects fall here, on Earth's surface. The numbers matched perfectly. When you account for the distance difference, the force pulling an apple is the exact same force holding the moon in orbit. Revolutionary. Heaven and Earth. Same physics. For 200 years, this stood as one of the greatest achievements in human history. It explained everything. Ocean tides, the shape of the Earth, why comets return. It even predicted Neptune before anyone saw it, just from wobbles in Uranus's orbit. Perfect, beautiful, complete. Except for one tiny detail nobody could explain. The perfect coincidence. Here's that detail. Drop a hammer and a feather in a vacuum. They hit the ground at exactly the same time. The hammer has way more mass, so gravity pulls it way harder. But the hammer also resists acceleration more. And these two effects cancel out perfectly. Newton's theory requires two completely different properties of mass: gravitational mass, how strongly you attract other objects, and inertial mass, how hard you are to accelerate, and they're always exactly equal, for every substance ever tested, to insane precision. Why? Newton had no answer. It was just this remarkable coincidence that made the math work. Or was it a coincidence? Einstein's simple question. Early 1900s, young patent clerk named Albert Einstein asks a different question. What if it's not a coincidence? What if that perfect equality is telling us something fundamental? Here's his thought experiment. You're in a closed room, no windows. You feel your normal weight. Are you on Earth? Or are you in a rocket in deep space accelerating upward at 32 feet per second squared? Can you tell the difference? Drop something, falls to the floor, both cases. Throw a ball, curves downward, both cases. Stand on a scale, same reading, both cases. There is no experiment, none whatsoever, that can tell you which situation you're in. This is the equivalence principle. And if you truly cannot tell gravity from acceleration, maybe they're the same thing. The falling apple isn't falling. Here's Einstein's mind-bending insight. Objects in free fall have no force acting on them. Read that again. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in the space station, none of them experience any force, zero. They're moving naturally, following their natural paths. But wait, you're thinking, the apple is clearly falling. Yes, but what if the apple isn't accelerating at all? What if it's moving in a perfectly straight line and it's space itself that's curved? This is it. This is the revolution. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other things. They warp the space around them. They bend it, curve it, distort the geometry itself. The apple isn't being pulled down. It's following the straightest possible path through curved space-time. But space-time near Earth is curved, so straight points toward Earth's center.
You're accelerating right now. You standing there? You're not being pulled down. You're trying to follow your natural path through curved space-time, a path toward Earth's center. But the ground is in your way. The ground pushes you upward, constantly, preventing you from following that natural trajectory. That's what you feel as weight, not gravity pulling down, the ground pushing up. You're like someone standing in an accelerating rocket. The floor pushes, you feel weight, not from any downward force, from being accelerated away from your natural path. The apple hanging in a tree is also being pushed upward by the branch. When the branch breaks, the pushing stops. The apple is suddenly free to follow its natural path through curved space-time. It falls. But the apple isn't accelerating. The apple is finally free to move naturally. You, standing on the ground, are being constantly accelerated upward by the floor pressing against your feet. Falling is the natural state. Standing still requires a force. That's the revolution. Einstein made a prediction. If gravity is really curved space-time, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't touch it. But if gravity is curvature of space itself, then light following a straight path through curved space should bend. Solar eclipse. Astronomers measured star positions near the sun's edge. The stars appeared shifted. The starlight had bent passing near the sun, exactly as Einstein predicted. Newspapers around the world announced it. Newton overthrown. Einstein became the most famous scientist on Earth overnight. Astronauts aren't in zero gravity. You know astronauts floating in the space station? Zero gravity up there, right? Wrong. Dead wrong. The gravitational field at the altitude of the ISS, about 250 miles up, is almost as strong as down here, about 90% as strong. So why do they float? Because they're falling. The station is falling. Everything is falling toward Earth constantly. But they're also moving sideways at 17,500 miles per hour. As they fall, Earth's curved surface falls away beneath them. They keep missing. They fall around Earth instead of into it. Everything falls together at exactly the same rate. So there's no sensation of falling, no weight, no up or down. It feels exactly like floating in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating freely Because they are the same thing. In free fall, no force acts on you. You're following the natural geometry of curved spacetime. Once you understand gravity as geometry, extreme stuff makes sense.
A massive star creates a deep well in spacetime. When it runs out of fuel and collapses, if it's massive enough, spacetime curves so sharply that all paths lead inward. Even light can't escape. That's a black hole. Not some mysterious cosmic vacuum cleaner, just a region where spacetime is curved so severely that the straightest paths all point inward. We've now detected gravitational waves, ripples in spacetime itself when black holes collide. We've photographed the shadow of a black hole, all predicted by Einstein's equations. The same principle explaining how an apple falls also explains the most extreme objects in the universe. Newton's equations still work beautifully for practical purposes. We use them to launch satellites, predict eclipses, navigate spacecraft. They're simpler and accurate enough for most things, but Einstein revealed what gravity actually is. Not a mysterious force pulling objects together across empty space. The curvature of space and time themselves. Mass tells space how to curve. Curved space tells objects how to move. When you step on a scale, you're not measuring a downward pull. You're measuring how hard the scale must push to prevent you from following your natural path through curved spacetime. When you watch something fall, you're seeing an object finally free to follow the geometry that mass has woven into the fabric of reality. When you look at the moon tonight, you're seeing an object following the straightest possible path through curved space around Earth, a path that looks like a circle because space itself is curved. Space curves. Objects follow those curves. That's what we call gravity. Not a force, geometry. And that is far more beautiful than any mysterious pull could ever be. Right now, you're not sitting still. You're accelerating upward. The ground is pushing you. Space is curved beneath you, and you're riding that curve through the cosmos at incredible speed, following the geometric paths that mass and energy have carved into the very fabric of existence. You're not standing on Earth, you're surfing space-time, and now you know it.